Okay, in this next section of the notes, we're going to talk about substitution methods. And if you remember, when we're dealing with polynomials, we can evaluate a polynomial function. And what we always said to remind you of is whenever you evaluate a function is that you're basically substituting something in some value for the variable, so for the missing variable. So when you evaluate a function, what you're trying to do is you're trying to find the value of that particular function when given a number for the missing variable. Now, this has always been done in a direct manner, where what we call direct substitution to evaluate will give you a value for the missing variable, and at that point you would plug in a value of 3, in this case for x, in every part of the function. And so then we would just basically punch that into our calculator and get a value of f of 3. Now, if you recall, when we plug in a value for x and we come up with a value of f of x, remember, f of x is the same thing as y, so you're just creating an ordered pair whenever you evaluate a function. And so in this case, when we plug 3 in for x, the value for y, or the value for f of x, is 98. So that's just some random point that satisfies this function, and so that would be a solution to the function, which means it would be a point on its graph if we were to eventually graph that. So when we evaluate a function, in this case we're dealing with polynomial functions, we're just simply doing a glorified t-chart. We're plugging in a value for x and getting the value of f of x out of it. Now, we're going to show you another method to do this, and this second method may seem a little strange at first, and it may seem a little time consuming, but it's going to be a very, very important process in a problem that we're going to work later. And you may not feel the need to learn how to do it here because it seems easier just to use direct substitution. But trust me when I tell you that this process is going to be extremely important in later notes, because it will make those problems a little bit easier. Now, this method is what we call synthetic substitution. So we're going to go through this process of setting up the synthetic substitution. I'm going to do this on the side so you can see what it looks like when you start, and you can see where all these numbers came from. First and foremost, in order to do synthetic substitution, all variables must be accounted for. And what do I mean by that? Well, notice here that x to the third is not in the original polynomial function, but we need that 0 that goes with x to the third to make synthetic substitution work. So we have to account for that. And so then what we're going to do is we're going to take the coefficient for each variable out of the polynomial function. And so you can see it gives me a 2, a 0, a -8, a 5, and a -7. So I'm just going to show you how this looks when you first start without all the numbers in it. Okay, so I've got the number in front of each variable there, and I'm going to draw this little kind of half box here. And you can see here this says x equals to 3. So I'm going to put this 3 on the outside. And so now I've got the preliminary setup of synthetic substitution. Now, the very first step in this is to drop my 2. Okay? And so what I'm going to do here is I'm going to take the numbers on the outside. I'm going to take the 3 and the 2, and I'm going to multiply them together. And from there, I'm going to bring that value of 6 right up there. So that's 2 times 3, which is right here. It's what we're evaluating. Gives us 6. Then I'm going to combine the terms together. So 0 and 6, when you combine them together, gives you 6. Again, I'm going to go through the same process as we did before. Instead of 2 times 3, now I'm going to do 6 times 3, and I'm going to bring that number in here, which is going to give me 18. And I'll combine 18 and negative 8 together, which is going to simply give me a positive 10. Again, I'm going to take positive 10, I'm going to multiply it times 3. That's going to give me 30, so I'm going to move that number in there. And I will combine terms again, so 5 and 30 is 35. And then lastly, 35 times 3 is going to give me 105. And when I combine 105 with negative 7, I get 98. And that last value represents the function when x is equal to 3. So you can basically say that f of 3 is equal to 98. Now, if we go back up here and we look at our direct substitution, that was the exact same answer that we got. Now, I know most of you are probably thinking that's a lot of trouble to get the same answer that I could do with my calculator using direct substitution. But the only thing I can say is that you need to learn this process, and you need to trust the fact that we will use this process for much more difficult problems later. So we're just trying to create a connection for you right now in working this process and how it connects to substitution. So you will be required on the test to do two types of substitution. Direct substitution, where you plug it into the function and use your calculator. So this is, you're simply going to use your calculator. And synthetic substitution, where you have to set up this process without variables and come to your final answer. So let's take a look at the next problem. Sample problem number 2. Go ahead at this point and pause the video and ask you to evaluate this polynomial function using both direct substitution and synthetic substitution. So go ahead and do that at this point now. Okay, so let's take a look at this first one. They're asking us to evaluate the function for x equals to 4. And so we'll simply just plug in 4 for all values of x. So f of 4 equals 5 times 4 to the third power plus 4 to the second power minus 4 times 4 plus 1. And you can see here where we simply substituted 4 in for all of the x values. Notice that I use parentheses. This is extremely important, if you recall, to whenever you use substitution, to use parentheses. So if you're dealing with negative numbers, that you raise it to the power correctly. Now, at this point, we'll just simply use your calculator. And if you use your calculator, you're going to get f of 4 equals to 321. Now keep in mind, f of 4 is just a naming mechanism. That is not, we're not solving for f. We're not going to divide this by 4 or anything like that. We've just created the point 4 and 321 on that polynomial function's graph. Now, we're not going to worry about graphing these polynomial functions at this point. That'll be something you'll do in a later class. But you do need to recognize that whenever you evaluate an expression or a function, that you're in essence just getting a point on the graph. So now that's direct substitution. So now we're going to work on synthetic substitution. So the first thing I need to do with synthetic substitution is I need to take the variables, and I'll go ahead and rewrite my function right here. Make sure that they're all in order, and make sure that I have them all accounted for. So that's x to the third, x squared, x to the first, x to the 0. And so now what I'm going to do is I'm going to just drop these values, and that's an understood 1. And I'm just going to drop these values down into a box that I'm going to create. And again, we were evaluating this function for x equals to 4. So so the 4 is going to go on the outside. My first step in this process is to drop the 5 down to the outside of the box, and that'll be my starting place. And I will multiply the 5 times the 4. So 5 times 4 will give me 20. So I'll put that value right there. Now I'm going to combine the terms. So 20 and 1 is 21. Next thing to do is to multiply 21 times 4, which is going to give me 84. Again, I'll combine like terms. 84 and negative 4 gives me a positive 80. And then 4 times 80 is going to give me 320. And lastly, we'll combine terms, which will be 321. So we can say that f of 4 equals 321. And of course, if we look back up here, that's the same thing that we got through direct substitution. So we've now done the same problem using both direct substitution and synthetic substitution, and you need to know how to do both of these processes correctly. Alright, lastly, we can see that substitution methods are viable ways to work word problems. So you can see here in sample problem number 3, it says that we have a shopping center. The number of shopping center space that we have in the United States can be modeled with this polynomial function, and they want to know how much retail space there was in 1990. So go ahead and pause the video here and see if you can figure out how to substitute into this polynomial function and come up with a final answer. Okay. The first thing we need to do here is we need to recognize that the model represents retail space from 1972 to 1996. And we're talking about 1990. And the t value in the function represents the time in terms of years. So we need to figure out how many years we're dealing with first. So 1990 minus 1972, which gives us a t value of 18 years. So I need to start. In this case, we're going to use direct substitution. Little hint for you would be the easier way to do this. So I'm going to say s is equal to negative 0.0068t, which is 18, cubed, minus 0.27, 18 squared. Run out a little space here. Plus 150t, which is also 18, plus 1700, and you can see we've directly substituted 18 years in for all of the t values. Now, at this point, I recommend you just go ahead and punch in this into your calculator, and what you're going to get is this. You're going to get 4272.86. Now, let's talk about what that number represents. You can see it says that S is the amount of retail space in millions of square feet. So that's in millions of square feet. So if I wanted to write that as a full number, then I would make that into millions. And so 4272, and then of course from here, from the decimal point, I would want 6 place values, and of course we have to start with the 8 and 6 and 0, and then 3 more zeros, and so that would give me my millions. And so here you can see that we had 4.2 trillion square feet of retail space in the United States in 1990, and I'm quite sure that we have a lot more than that nowadays as well. So that is an example of how we would use direct substitution to answer a word problem. Okay, so this has been a good review of some things that you should have known from previous units. Identifying polynomial functions and substitution, and then of course we introduced synthetic substitution for you as well. So be sure to learn how to do that before we move into the next set of notes.